Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our learning on enhanced oil recovery, especially about the simulation. So we will perform the EOR simulation using tNavigator software. We will use case example from tNavigator and hopefully we can learn a lot. But before that, I just want to remind you, if you like or if you find this channel or this video useful, please don't forget to subscribe, leave comment, and press the like button. Okay, so thank you, and let's go ahead. So this is the case example from tNavigator. As usual, we will start by introducing the model. This is our pressure map in 2D map, and this is the 3D model. Looks good, right? And you can see we have 1, 2, 3, 4, 5, 6, 7 producers and 1, 2, 3, 4, 5 injectors. Okay, so in this video, we will perform enhanced oil recovery using polymer injection. Later on, we will expand the case by also performing surfactant and alkaline injection. So basically, we will in the future perform ASP, enhanced oil recovery, alkaline, surfactant, and then polymer. Okay, so in this case, we will only perform polymer injection. So we expect that the mobility ratio will be improved when we, inject the polymer. Okay. Okay, so this is the model. We can also review the block size in Y direction and in Z direction, right? And then the depth around this depth, okay. The top there, net to gross, okay. And then porosity and permeability along X, along Y, along Z, standard pore volume, okay. And then pressure like this, saturation of oil, okay. So this is our oil zone, and then below that we have water zone, okay. And other properties, okay. And then let's check the data set as usual. Okay, let's review. Actually, I think this is just, a normal, usual data set that we have already in the past. So we start by run spec as usual, title, start of the simulation, well dims. I don't need to repeat again what well dims is. Water phase, oil phase. Okay, so something that is new for us is polymer injection. So the keyword polymer here will tell the tNavigator that yes, we will use polymer here. Okay, so water, oil, and we will also inject polymer. We will have polymer in the model. If we want to inject alkaline and surfactant, we will also add more keywords. The keyword is surfactant and then alkaline. And then this is not really necessary, I think. Unifin, Unifault, as usual. Field unit, grid optimization, yes. This is 43 is number of blocks in X direction, in Y direction, and in Z direction. And this is the maximum number of faults that we have in the model. This is the data, the setting for the data table, setting for the regioning, for the equilibration, and this is for the aquifer. Okay. And again, we will take information for the grid from this file. Later we will check and then edit props. Props will be very, very important. And we will take the properties from this. And then region, we only have one region, set num, here, based on saturation number. But when we perform surfactant injection, we need to make more regions to specify that in some area which has, high surfactant concentration, there will be another relative permeability that we will use in that high concentration zone. So basically we will add more region, but maybe in the future we'll talk about that. And then solution, under the solution we have something to define the equilibration, and we defined it here. So if you want to check, equilibration must be in fluid properties, equilibrium. So the data on the table there is taken from here. So the depth, 2001 here, the depth, and then datum pressure, 1364 there, and then the gas water contact or water oil contact at 2162, and everything will be set or will be filled or populated with default if you close with slash. So basically 0000 and then other stars. Okay, let's confirm that indeed our water oil contact is around this depth. So 2162, and right here. So I touch the grid block and you can see the depth here, right? 2128 and this one 2196. So between that must be the oil water contact around 2162. Or we can also go to 2D map and then we can check the layer. Yeah, the JK, I mean IK. So here the oil water contact is around 2100 and then move like this. The oil water contact locally here is around 2187. Okay. So by defining the equilibration here, there we will have the oil water contact established throughout the reservoir. Okay, and then go back to average 3D there at this depth, our oil water contact. Okay, and then summary as usual, schedule will be taken from this. Schedule will be important because we will provide the information for the polymer concentration from the include file of the schedule. And then N as usual. Okay, and then let's go to grid. Let's see if there is something special. Most likely not. Okay, this is just for the access. This is the fault that we have. Okay, do we have the fault here? Let's see. Okay. From quick review, I still haven't found the fault. Okay, whatever. Doesn't matter. Anyway, okay, so fault. You can see here we set our fault. And then we go to, what is this? Okay. Doesn't matter, I think. Yeah, this is basically about our grid. Everything here is about the grid. And pinch, init, Eng-Man, right? So basically we define cells that are active and inactive. Okay, active will be valued 1 like this, 1, and then inactive will be 0 there, 0. So that's for the Eng-Man. And what else? Yeah, this is inside the grid. You will always find this type of configuration of data will be massive like this if it is a real model. Okay, but that's not the point of this exercise. And then let's continue to props, which is very important. Okay, no echo is actually not very important here. Okay, we can neglect this actually. And then SWOF, this is actually relative permeability table. This column is water saturation, relative permeability for water, relative permeability for oil, and then capillary pressure. And then density for oil, water, and gas. And then this is for the dead oil with constant compressibility. And then this is the PVT for the water, reference pressure, formation volume factor, compressibility, and then viscosity. And then rock compressibility, the keyword is rock. And then this is very important for polymer injection, PLY adds. This is actually to specify polymer adsorption. Okay, so that's why we have local polymer concentration here for the first column, and the second column will be adsorbed polymer concentration. Because when you inject polymer, some polymer will be adsorbed on the pores. Okay, which basically when we inject alkaline, we will reduce the polymer adsorption, which will improve the performance. And then you have also there a new keyword for us, ply rock. This keyword actually specifies rock properties for polymer flood. Okay, and you will get this kind of information, of course, by laboratory. So the first column will be dead pore space. And then number 2 here must be residual resistance factor for this rock. And then this will be mass density of the rock, adsorption index. 1 for desorption can take place if polymer concentration decreases in the grid block. And 2, we will prevent desorption. Okay, so if you select 1, if you choose and type in 1, desorption, the desorption of polymer can take place if polymer concentration decreases in the grid block. But if you put 2 there, then basically all the polymer will be there. Not all, but the adsorbed polymer will be there. There will be no desorption. Okay. And lastly, it is maximum polymer adsorption value in kilogram per kilogram or pound per pound. Here, basically we have 2 package because the data set, the case actually for 2 regions case, where in region 1 will be, will not be, will not consider anything about surfactant, but region 2 we will consider surfactant. But actually that's for the later case. Still we maintain the 2 region in this case, but because we do not deal with surfactant, the 2 regions means nothing, right? The 2 regions will be meaningful where when we have surfactant later on. But because here we only have polymer, it will be nothing. And even in this polymer and this keyword ply rock, you can see the same exact value. And here, if we check the fluid properties For the relative permeability, we have two regions, but region 2 will be only meaningful in, high concentration of surfactant. But because we don't have any surfactant here, so region 2 will be meaningless. And only region 1 will be, applicable. And then PVT for water, PVT oil, this one. And we have the data here, the setting there. Pressure, formation volume factor, and viscosity. 85.8, the dead oil viscosity. Raw compressibility, density, and again, relative permeability. This one is, this equilibration. We talked about that already. And then here also we have for ply adds, we have two package because we have two regions, but basically they are the same. And then we have ply fisc. Okay, you can see there it's talking about viscosity. Okay, so ply fisc is polymer concentration and water viscosity factor. Okay, so if you add polymer and there will be change in water viscosity by the factor of this, right? Okay, continue. And we actually have another keyword, ply shear, this, but currently it's not applicable in this case. So that's why we put there. This keyword actually specifies polymer shear thinning data. So if I may add here, specifies polymer shear thinning data. If you have from your laboratory, we put it here. All right, and then we also have ply max. Okay, ply max. So this is the polymer concentration, and then the salt concentration there. Okay, so basically ply max is, let me put it here, specify polymer and salt concentrations for mixing calculations. And lastly, this is the Toth Longstaff mixing parameter. Okay, we defined it using this keyword. Okay, so as you can see, property section is very, very important, right? All right. Okay, so we will continue. And then we go to summary. As usual, inside summary, we find here. And then schedule. Schedule also very important. I will not explain again about well specs, the location of the well, and then the completion. Okay. And then, yeah, this is comdat for, so it will be completion data for each block. You see here, injector 3 located, or the completion is located at these cells, and then control for the injection rate or injection operation, and then the production, and then the dates for our time steps of calculation. And then we will put our injector concentration here, W polymer. So injector 1 will inject polymer, and this is the concentration. Okay, so that's for the W polymer. And the unit will be, in this case, field unit, pound per stock time barrel. Okay, so this is 0.35, the concentration of the polymer, 0.35 pound per stock tank barrel. And then time steps again. And then we increase the concentration of the polymer and then go down. Okay, so there, let's see, control find W polymer. This one 0.5, the first one 0.3. Okay, so only that. Okay, so that's it. And then as usual, let's perform the calculation, the simulation. Okay, we can see here graphs, the oil profile, water profile, or maybe I don't know, I'm not interested in water profile, but instead, let's see the injection profile. Okay, here. Okay, so for the injector, basically, let's check the schedule. Open, and then here. So the polymer will be considered in water phase. Okay. Here we are looking at that, the production and then the water injection profile. And then we can also check the tracer, or maybe here we can see increase. And maybe we can check the tracer here. You can see we have polymer there. If you expand, you have injection mass concentration, injection mass rate, mass total, mass absorption. It's very, very interesting. If you expand, you can check the profile for each injector. Injector will only give you, injection profile, injection mass rate, injection mass concentration, injection mass total. But producer will give you production mass rate, production mass concentration, production mass total. But if you check on this one, then you will show everything. Okay, and then we can also check here ASP flood tracer polymer. Okay, 2D, you see there. Make sure you are checking the average, and we can also check or make, this, the cross section. There you can see. You can also create average, and then if you're interested, profile to connect like this, and then this. It's just random shape, and then yeah, apply, and then check it here, profile, if you're interested. Okay, and 2D, I mean 3D, it's like this. And then check PVT region, we only have one, saturation region, rock compaction one, polymer mixing one, active grid. Okay, so basically we only have one region for everything: PVT, saturation, rock compaction, equilibrium, polymer mixing, active. That's why in fluid properties, having two regions, relative permeability here is, meaningless. And go back to schedule, or not. Schedule already defined in dataset, schedule dataset. I mean graphs. So if you check here, let's check the polymer injection. Uncheck here. So basically we increase the injection mass rate at this date, or maybe we can also refer to the schedule. We start injecting polymer at what date? Let's search W polymer, January 2018. Actually starting from the 2018. And when did we improve the concentration? January 2018, and then we increase after December 2024. So that's why, yeah, right? December 2024, that's why we increase the injection concentration of the polymer at December 2024. And that results in increase of production, or not that, but yeah, 2018, we start injecting the polymer, and you can see here, production increases. But in 2024, December, the production increase is not significant, but you can see the decline is not very low. So we actually basically, you can check it, we improve the decline. We decrease the decline rate. Maybe that's because the effect of the polymer. You need to make sure. You need to make sure that. So here we have fast or rapid production decline, but after we inject polymer in 2018 and we improve the concentration of the polymer in the end of 2024, first we have production increase, and maybe you can say that the decline is being mild here. So we arrest the production decline. Okay, so this is the total analytics, pressure, all right, and then again tracer. You can also check the production. So you inject some of the polymer, but you also produce some. And there will be some polymer that is adsorbed. So you can say basically they are lost because they are adsorbed on the pores and you cannot recover the polymer. And you can check the adsorbed polymer in this one. Okay, so you can check the polymer concentration. Let's check the 2D map. Okay, and this is the palette showing you the concentration in pound per stock tank barrel. This is the maximal polymer concentration, and then adsorbed polymer concentration. But the value is not very high because this is the maximum polymer adsorption. We already set that in properties, not in Polymax, but I think it's in Polyrock. Okay, so the value is quite small there. Okay. Oh, I mean, yeah, sorry. Imply adds. So local polymer concentration and the adsorbed polymer concentration. So we define the distribution of adsorbed polymer using this keyword apply adds. Okay, so that's it. Later maybe in the next video, I will compare it with the case where we only perform water injection. So I will decrease the polymer concentration down to 0 pound per stock tank barrel. So basically no polymer inside our water injection, and let's see what will happen. Of course, we expect that the production will be lower than the case of polymer injection. Okay, so go back here if you want to check for the last time. Good. The effect of, the effect of polymer. Okay. And then tracers. And lastly, the polymer concentration. Okay, so that's all. I hope you enjoyed this video. I hope this video is useful. Thank you so much for watching, and don't forget to press subscribe, like, and you can also leave your comment. Okay, so thank you and see you again in the next enhanced oil recovery videos. Thank you.